All right, thought I'd make another video solution here. How about chapter 33, number 58. It's kind of a long problem with a bunch of parts to it. And it begins by just simply says this. It says, excuse me, it says in the circuit shown in the figure. And so I went ahead and I printed up, here's the circuits. We have our AC source and our series LCR circuit with some switches in here. It says, assume that all the parameters except C are given. All right, so, you know, we know the R, we know the L, we know the maximum voltage, and we know the frequency. That's the given here. We don't know the C, and that's fine. I think that's one of the questions, to find C in terms of some parameters in here. And it goes on to then say, and here's question A, find the current as a function of time. Now, maybe the first thing to go through is kind of this loop right here. Because what would we do if we had a switch? And so we have an inductor and then a switch. And over here we have a capacitor and then a switch. When it's open, obviously the current just has to go through the inductor. But what happens when it's closed? Does it split and go half through the switch and half through the inductor? Now, we saw ones like this for resistors. In fact, maybe it's a little easier to kind of deal with this in terms of resistors. So maybe I'll just kind of make a simple circuit where what I have is a wire that short circuits a resistor. And so the current's coming in here. I won't even worry about the rest of the circuit, but if I just did a loop here, and so let me call this point A, point B, point C, and point D, and I do the loop A to B to C to D and back to A. If I say the current comes over here and say, okay, current number 1 goes this way, and then through the resistor is current number 2, as I add up the sum of all the voltage changes from A to B would be nothing. And here's the key part, B to C would also be nothing, no matter what current number 1 is. C to D has nothing in it, so that would be nothing. And then finally, D back to A would be going against the currents, would be a plus, and it would be I2R, and all that would have to add up to 0. But the point is, if you didn't see it back in chapter 27 and 8, when you have a loop like this, when you just have a wire, then once you do the conservation of energy, that's the Kirchhoff's loop rule, there would be no current through there. So for this problem to make any sense here, you need to realize that if you ever have just a bare wire going like this, in other words, what we call a short circuit, the object that has an element in it. Now, I just did it with the resistor, but we could also do it with the inductor, and of course, then we would have something, you know, like a minus, or would go the other way, so it would be plus L di dt. But you're still going to get the conclusion that there would be no current through there. So here's what I want to start this problem with, is to get you to realize that when they have these switches closed, the current's going to go through the resistor, then all of it. See, this is what we mean by current number 2 is 0. That means current number 1 is all of it. All the current will go through switch number 2, and then all the current will go through, switch number 1. Then all the current will go through switch number 2 and then back. They'll just completely bypass it. And so this circuit at this point really looks something like this. That's what it is. It's just a resistor and an AC power source. So I don't know if I needed to explain that, but that's important to connect because then later on they're going to open these switches, and then of course then it all goes through. Like if you open switch 1, it all goes through that inductor. And if you open switch 1 and 2, it goes, it's a whole series LCR circuit or RLC circuit where it's got to go through all of these, okay? So keep that little principle in mind. I'll come back to the picture if need be, but that really helps with part A, which says find the current as a function of time. So the current, as we know, would be the voltage divided by the, in this case, the impedance, if you even want to call it an impedance. It really is just a resistor at this point. So I don't have to do anything fancy with the Z and the square root and all that stuff. I just got to divide it by the resistance. Now, the voltage, as it says in the diagram here, where the diagram go, there it is, would be then what they call delta V max cosine omega t divided by R. And so that would be the end of step A. It's just, hey, that is the current. All right, so then step 2 says find the power delivered to this circuit. Well, again, the power would, again, just be simply no inductors, no capacitors, the simple thing, just a resistor. Now, as we hopefully caught, when you go to calculate the power, and let's see, do they use the word average power? Find the power delivered. Well, they really should say the power averaged over a cycle, so over a long period of time in average, because the current's going to go up and down and up and down and up and down. So there's going to be like a lot of power, a little power, a lot of power, a little power. So they didn't really say instantaneous power, although they just say power, so I'm a little confused if they want instantaneous power or average power. So maybe I'll do both. If they wanted instantaneous power, it would be the current at that particular moment times the voltage at that particular moment. And as we see here, the current would be this maximum divided by R. Times cosine omega t. And the voltage would be delta V maximum times cosine omega t. And that, of course, comes out to be delta V maximum squared over R and a cosine squared omega t. So if they mean the instantaneous power, this would be the answer. And of course, it would change with time. And it makes sense, because if you plotted power versus time, you have this cosine squared function, which would look like this, which goes up to 1 and down to 0. And so if you averaged it, you would, of course, get 1/2. So you could write power equals to delta V max squared, and then there's the 1/2, or if they're looking at average power. And they usually are when they say something like that. So I have a feeling that's what they were expecting me to write. And I guess I could also do something like this. I could write it as maximum over the square root of 2 and another maximum over the square root of 2 times a 1 over R. And that way it becomes VRMS squared over R. And so that or that or that is probably what they're looking for. In fact, let me switch over here to the solutions and see what is the author saying. And it looks like he's got this right here. Okay. So that's what they want, is average power. And either one of these would be great. And then instantaneous power would be that. And should have been a little more clear, but that's fine. All right, well, continuing on here, what does C say? C says, find the current as a function of time after only switch 1 is opened. Okay, so coming back to our circuit, if we open switch 1, then now we have an inductor in here. But the thinking is still the same. That is, I would have the current. It would be then the voltage divided by the impedance. And of course, this time, the impedance is more than just the resistance. And the impedance is the R squared, and then the reactance of the inductor minus the reactance of the capacitor squared, and then square rooted. Now, of course, for this case, we still have switch 2 closed, so we can ignore any effect of the capacitor. So this would just be the voltage divided by R squared plus the reactance of the inductor squared and square root. So we've got two elements, right? The resistor and the inductor that is opposing the current. Now, to write it in the form that they gave us, that's kind of the general rule here, is that we would write this then, the voltage is a function of time, and it's a maximum, and then it is cosine omega t, but as we hopefully learned, it will be out of phase. This is that phase part. The current is out of phase compared to the voltage. And then down here would be this R squared, and I'll just write this as omega squared L squared. And of course, then the phase we learned, the cosine of the phase is this XL minus XC over R. But again, we're not dealing with a capacitor. So the phase would be the inverse tangent of omega L over R. And so maybe I'll put page 1 in case I need to come back to this. But putting that all together for a final answer of C would say that the current, as a function of time, then, would be the maximum voltage divided by the impedance, which would be the square root of this R squared plus the omega squared L squared. And then we would have this cosine. There's the omega t. And the phase we just did would be this inverse tangent of omega L over R. So that would be, in terms of symbols, obviously we can't give a number here because we don't have any numbers. So we're asked to put it in the symbols of the things we're given. All right, so now if I go to D, D says, now after switch 2 is also open. So it's important we read it, that word also. So in other words, both 1 and now 2 are open. So I'll put a little C here for the capacitor. So now I'm finally to the full circuit that we were studying in this chapter, the series RLC circuit. So here it is. And let me go back to D. What does it say here? Okay, after switch 2 is also opened, the current and the voltage are in phase. Find the capacitance. All right, so in phase, let me come back to page 1 here. This is our phase stuff. So maybe I'll just say here is the XL minus the XC. So these are the reactants between the inductor and the capacitor, and the effect of the resistor. And if they're in phase, then we're talking about the tangent of 0, which is 0, which means XL minus XC is 0. We can divide by the R and then multiply, but that just means XL is equal to XC. Oh, which is how we're going to answer this, because this is omega L, and this is 1 over the omega C. In fact, this is what we call the resonance condition. So hopefully you recognized that right from the beginning, and you didn't even have to derive this. You just said, oh, well, yeah, if they're in phase, these two have to be equal. The reactance of the inductor has to equal the reactance of the capacitor. So omega squared would be 1 over LC, and I'm sure you've seen this way too many times, or hopefully it's beginning to sink in, that then the frequency, at least the angular frequency, would be 1 over the square root of LC. Oh, and that's Sorry about that. I was thinking that was they asked. But they asked for the C, so let me redo this. They asked for C, and so that would be 1 over omega squared times L. So there would be the answer for D. What is the capacitance of this, or, the necessary capacitance here? Now I flip over to the answer. I see the author put an omega naught, and that's not too bad because that's normally what we do, but this problem doesn't have a omega naught in the symbol. It just says this is the frequency. So I would prefer not to have an omega naught. The answer is always supposed to be in the terms of the stuff given, and they're kind of implying that the stuff given is the L, the R, and the omega. But that is also the standard symbol for the resonant frequency. So I see why the author did that, but probably not what I want to do here. So I'm going to leave it as an omega. E, what does E say here? Find the impedance of the circuit when both switches are open. Okay. Now remember, this impedance is this R squared plus the reactance of the inductor minus the reactance of the capacitor. But again, they made it very clear that when you have both of these, they are in phase. That was back to D. So if we go back to D, being in phase means they're equal to each other, and that's how we got the value of the capacitance, so that they were in phase, but that would just go away. So there's really not much to do for E other than to recognize that these two would be equal and opposite. That's what the part D was implying there. So the impedance is really just the resistance at that point here. So that's probably the easier of them. Now F says, find the maximum energy stored in the capacitor. Okay. So the capacitor is going through this oscillation, and that is it building up charge and then diminishing and building up charge the other way and then diminishing and building up charge. So, okay, I guess then for the maximum energy, so I'll say U, maybe I'll even put a maximum. Maybe I'll put a little sub E, because the energy in a capacitor is in the form of an electric field. That's why we did capacitors first way back with chapter 26. And we're introduced to capacitors when we started dealing with the energies in the electric field. And so if we're after the maximum, if you remember, it's 1/2 CV squared for the energy in a capacitor. So when they have the maximum voltage, then we are going to have the maximum energy. And of course, voltage and current are not in phase. Well, they are in phase, and for at least at the moment. But when you go to calculate the maximum voltage, and we're talking about the capacitor, this would then be the maximum current times the reactance of the capacitor. So that's our Ohm's law as applied to an AC circuit. Current times, and I don't want to say resistance, but current times resistance is voltage. Now we don't have resistance for a capacitor, it's a reactance. So, but it's the same idea that for Ohm's law, current times the reactance is the voltage. So this would become 1/2 C, and I maximum really comes back to here. Actually goes even further back. Didn't we do I maximum somewhere? Well, back at A, this then, without the cosine, this would be that maximum. Okay. So this would be V max divided by R squared. That would be the current squared. And then we have the reactance squared. And the reactance of a capacitor is 1 over omega c, so we could square that. Now, I think we've got some more algebra we could do to simplify this. Let's see, where am I? Page 3 here. But if we take this, and I'll just write U for the energy maximum, comma E for electric, we would have this 1/2. And I guess I'll just put 1 over C here, because this C would cancel with 1 over there. I'm going to write this V max squared over R squared right here. But watch this. This is a 1 over the omega squared. And coming back to here, or really here, omega squared is 1 over LC. So I could replace this 1 over omega with LC, and thereby canceling off the C's, and get then, let's see, a 1/2, an L, a V maximum squared over an R squared. And so that would be maybe the simplest form. Guess we could have left it, well, we don't want to leave it as maximum because that's not given, but could have left it maybe here, but again, they go to imply that C is not given. So you want to put your answer in the stuff that's given. When you don't have numbers, I should say that. Some of the harder physics problems are when you don't have numbers and you're just working with symbols, and that's what we have in this problem. And the general rule is you should give an answer in the symbols that were given in the problem. So given in this problem, the symbols were things like maximum voltage, omega R, and L. C is not. So that's why it would be a little inappropriate to maybe stop right here or even right here. And that's why then eventually I got rid of the C, which happened to get rid of the omega. But that wasn't, I don't think, a requirement because that's given in the problem. We can have an answer in terms of omega and R's and L's and V max. That's the given stuff. Anyway, so that's why I feel like I need to make this next step. And then once you do that, you lose all the C's and kind of forget you're even working with a capacitor. But it looks like we're working with an inductor. And I think that's actually the next question. So that's F. Let's go on to G, because I think G is saying, yeah, find the maximum energy stored in the inductor during these oscillations. Now, again, we're at resonance, so what's happening is the energy is going from the capacitor being filled to the inductor being filled, and it's just swashing back and forth between this electrical energy and this magnetic energy. So one thing that I can just say from the get-go here is whatever energy I just calculated for the capacitor gets sloshed over to the inductor. So really, G is just same. I don't really need to do anything for G. That's the answer. Whatever I got for the capacitor is also what I'm going to get for the inductor. However, maybe I should work it out. So let me say U, and as I said, find its maximum. And let me put a little sub B, because the energy in the inductor is stored as a magnetic field. So the energy is sloshing from an electric field in the capacitor to a magnetic field in the inductor, and then back and forth, back and forth, back and forth. It's like in Physics 121 when you did the pendulum, or no, I guess that's in 123. You did the spring. You did the spring going up and down, and it was, a combination of potential energy in the spring, kinetic energy, potential energy in the spring, kinetic energy, potential energy in the spring, then back to kinetic energy, potential energy in the spring, kinetic energy. And that's what we have, this oscillation of two different types of energy, and they each equal the same. So on a spring, the kinetic energy here equaled the potential energy when it got close, and then likewise when it went down, then the kinetic energy was the same as the potential energy, which is the same as the kinetic energy, which is the same as the potential energy. So they were equal to each other. Now, at different moments in time, they were never equal to each other at the same moment. That would be impossible because of conservation of energy. But they could equal each other in their maximum just at different moments in time. So when the capacitor loses or has no charges on it, it loses all of its energy. It's in the magnetic field in the inductor. So anyways, I hope you remember from our inductors a couple chapters back is that the energy is 1/2 Li squared. And if we're looking for the maximum energy, that would be associated when we have the maximum current. And the maximum current, as we just said, would be that delta V max over R. So if we square that, we have then this L in the numerator, a delta V max squared also in the numerator, and a 2R squared in the denominator. And sure enough, not a surprise, it is the same number. And so the F and G are the energies that in each of those elements, they're just at different moments in time. H goes on to say, now the frequency of the voltage is doubled. Oh, okay. So we are going to increase to a frequency that I will call 2 omega. Omega, again, still being the symbol that is the original frequency of this. You could also call it omega naught if you want. Probably the author does. I'll check that in a second. But he doesn't here, but it is a resonant frequency, so it would be, I guess, okay to call it omega naught. But I'm just going to call it now 2 omega. So H here. Now the frequency of the voltage source is doubled. Find the phase difference between the current and the voltage. So the phase is this tangent theta is the reactance of the inductor minus the reactance of the capacitor over the R. Now the reactance of our inductor is that omega L. Now omega being the frequency. So I'm going to write it as 2 omega here. That'll be okay. So that my omega is the original one. Okay, so this is the new frequency, this ... right there. So it's the new frequency times the L. And then this is divided by 1 over, and then the new frequency. So that'd be 2 omega C, where again, my omega is the omega of the old frequency. So this right here, I'll put a little dot on it, is the new frequency. And divide that by R. Kind of like it that way, but that's got a compound fraction, so I suspect that's not really a good way to leave it. Oh, and plus I know that omega is related to the L and the C. So why don't I keep going? So this is a 2, and then the omega is the 1 over the square root of LC, and then of course times that L, then minus the 1 over and 2C, and again omega would be 1 over, so I'm going to put that omega, which is in the denominator, that LC. So let me come back to page 2, but I'm really substituting that in. What I know is omega is equal to 1 over the square root of LC. So right there, that omega is 1 over the square root of LC, and that omega is 1 over the square root of LC, but a compound fraction makes it go to the top. Now let me not forget the R here. Let's see if I can simplify this a little bit, because it looks like one of the L's downstairs would cancel, leaving a square root of L. So this would be 2 times the square root of L over the square root of C. And then this would be, no, let's see, what is this? This would be, looks like a 2 would be left downstairs, but this square root of c would go with one of the square roots of c, if you think about c as being a square root times a square root. And then I have the square root of L. And that's a good sign because this numerator then is like terms. And it doesn't look like I'm going to be able to squeeze it all on here. But in the numerator, it looks like I have a common denominator of 2 times the square root of LC. And so to get this would make a 4 times the square root of L. To bring it to the same common denominator, I got to multiply by 2. And this already has that denominator, so it'd be minus the square root of L. Yeah, boy, this is getting long. Look at this, page 4. Okay, page 4. And so, where were we here? Tangent of phi then would be, and looks like here if I take a 4 minus a 1, I get a 3 times the square root of L all over 2 square root of C, and don't forget that's over R. Let me then, like any good compound fraction, flip and multiply, so this becomes 1 over R. And so the tangent of phi then is 3 times the square root of L times a 2, an R, and a square root of C. Yay! It actually asked for phi, so I guess I got one more step. Inverse tangent, or arctangent, of 3 square root of L over 2R square root of C. And so there would be the answer to, I think I was on H now, if I'm not mistaken what I put here. H, yeah, that's a terrible looking H. Looks like a B there. Okay, so there's my H, and I think, let's come back to the question, is that it? No, there's an I, okay, and so HI, I is the last one here. Find the frequency that makes the inductive reactance 1/2 of the capacitance reactance. Okay, let me read that carefully. The frequency of which the inductance is 1/2 of the capacitance inductance. I hope I read that right. Find the frequency that makes the reactive inductance, good, 1/2 the capacitance reactance. Okay, so if I write this as the omega L, now let me be careful because I'm looking for that frequency that does this. So this is not the omega that is given here. So let me call it something different. How about omega prime? Hope that doesn't look like a derivative. But I just want to indicate that there'd be some frequency, and that's what I'm trying to find, because it says find the frequency. So I'm trying to find that, where this would be true, that the reactance of the inductor is half the reactance of the capacitor. Okay. And the reactance of a capacitor is 1 over omega c. But again, let me put that as a prime. So I want to find these. So I'm going to move the omega primes together. So I've got the omega prime together, that's squared. And then I would have a 1 across the top, and I would have a 2, and then an L, and then a C. And so then if I take the square root of this, I would have 1 over the square root of 2, and then 1 over the square root of LC is this omega prime that I'm looking for. And I write it this way because, again, probably by the general rules here, is we shouldn't have an answer with a C in it because C is not known. The L, the R, and the omega and the voltage maximum are. So I'm going to write that as the original frequency omega. Maybe you can even write it as omega naught if that would be less confusing. And I bet the the author probably does. In fact, let me just kind of flip over. Where's his answers? Yeah, he does use that omega naught again, but that's probably not a good symbol here. I don't know if that's confusing or not, but let me just write it as the omega. So I would write this as the omega over the square root of 2. So the original frequency of this divided by the square root of 2 would be the frequency that would meet this condition where the reactant of the inductor is 1/2 of the capacitor. And of course, it is a lower frequency as we should expect because omega is the perfect balance where the reactants of the inductor and the capacitor are the same. And so if you want your inductor to be less reactive, we have to go to a lower frequencies where the capacitor dominates. So the capacitor is dominating by a factor of 2. If we went to higher frequencies, then the inductor would dominate. And that's what we did back in H, where we went to twice the frequency. And I think that's it, right? Yeah, okay. Hope that helps. Bye now.